you doing, Jesse? How you doing, Jamarcus? What should we do today? It is time for some questions. It is Thursday, or as we call it here, Hasm Friday, in picture-in-picture mode right there. Why do I have two chats? I have chat up from yesterday. I got yesterday's class chat up. Canvas content, quiz 8, conference roles. We got this. Let's do it. I bet people are going to be very happy with this one. Let's do it. Okay, Canvas content number 8. Canvas content number 8. Wow. It's one of the last two Canvas contents. We're getting close to the end of the semester right here. What's up, Jamarcus? Chapter 15. Put them in the chat. We'll get them done. Okay, let's do some Canvas content number 8 right here. Drop those questions in the chat. Gonna need some help with this right here. We got all those points. When I give out 100 now, people are probably like, 100 points? 100, Brian? Come on. So, stat 201, Canvas content 8, confidence intervals. Here we go. Let's preview it. Let's do it. Okay, so remember, the key is to understand what we are doing and why we're doing it. When doing a confidence interval for the mean, Jesse, do you know the answer right now? Just look down here. So if you practice the techniques we're doing, hey, Marcus, good to see you here. So if you practice the techniques we're doing, we have certain ways of teaching things. And Jesse knows instantaneously it's T. And the reason we know it's the T distribution is because Mr. T is mean if you're doing drugs. So we're going to show us right here. Let's go here to YouTube, Mr. T, PSA, drugs. Oh, did Key and Peele do it? Oh, they did a totally different PSA right there. Here we go. Okay. One of these, I swear, shows a random thing on here. Yeah, they did. Key and Peele apparently did some stuff. So here's Mr. T back in the 80s. There we go. I was showing the whole thing there? I don't know. Is it going to play? Oh, there it goes.
I get angry just thinking about it makes me mad. Little kids doing drugs, it turns my stomach.
That you don't want to see that, Mr. T. That is not happy, Mr. T. So with this right here, why do we say this? Well, we want to talk about the T distribution. So the T distribution is used for means. This is the Z. This is the T, the student T right here. And once again, we're on the apps. If you're watching this video, this is the apps right here, which allows us to do the T distribution and create confidence intervals with it. And so when we do the T, we'll go here to one of our millions of documents. The T interval is going to be Y bar, which is the sample mean, plus or minus the T with a certain amount of confidence, we put the star on it, n minus 1 degrees of freedom, S over square root of n. This differs from a proportion interval, which is P hat plus or minus Z star, and then P hat times Q hat over n square root. So the T is for means. Even when we get to the 2 sample T, it'll be Y bar 1 minus Y bar 2, the difference between the two means, plus or minus the T star with a degrees of freedom. That's a complicated formula. And then S sub 1 squared over N sub 1 plus S sub 2 squared over N sub 2. You do get a formula sheet for the exam. And then, Jesse, everything in green is known as the what with these intervals. Everything in green is known as the what, or Jamarcus, or Marcus right there. Everything in green is known as the what for those intervals. Everything in green is part of the what. Notice the pattern of how intervals work, because everything in green is what? Everything in green is the margin of error, exactly. And then everything I'm highlighting in orange determines the confidence level. So that's the confidence level right there of the interval. And then everything I'm highlighting in yellow is the what of the interval. Everything in yellow is the what of the interval. So the green is the kind of, Marcus, good answer. It's kind of the standard deviation. We call it the standard error now. So this is the margin of error. The yellow is the standard errors of the estimates. This gives the confidence level, and this is the estimate itself, which is the center of the interval. The center, the estimate, and these are the formats for all the confidence intervals. Great job, Marcus. Let's throw Marcus 500 points. This is the format for every confidence interval we'll be doing. Confidence intervals put a star on the T or the Z because it's based on level of confidence. And once again, notice we like to say, just to review again, Mr. T is mean. So if you're doing drugs, Mr. T is mean. So there you go right there. The T is used for means, just a way to remember it, a mnemonic that helps us remember Mr. T is the interval right here. So once we see this, interval for means, which of the following do we use? T. And we've really only done these right here so far, so you wouldn't even pick chi-squared or skewed. Well, we've done skewed, but that wouldn't go. Which of the following would you not use to check the nearly normal? So the nearly normal is part of what we just talked about, because the nearly normal is the third condition when what? The nearly normal is the third condition when what? I'm trying to find a sheet where we talked about this yesterday. The nearly normal is the third condition when what? The nearly normal for quantitative variables. So when you do something like here, like a quantitative question like we were doing yesterday, we first figured out it was quantitative. That's going to tell us the third condition. So if it's quantitative, what kind of data do we have? We have data that looks like this, like GPA, right? So when you analyze GPA, it needs to be blue. We go here to analyze distribution, and the first thing we see is a histogram. So histograms can be used. We can also do normal quantile plots, known as normal probability plots. Ooh, that's got some skew to it. We can also do a goodness of fit test right here by going over here and go continuous fit, fit normal, and it's probably going to fail the goodness of fit. We can also use large enough n. So this does fail the goodness of fit because of the low p-value. All those are chapter 5 topics which come into play right here, but which of these did I not mention? And then kind of think why. Which of these is not used to check the nearly normal, and then why? I'll explain the why if you want to know. So which one of these would not be used to check the nearly normal? So I just kind of went over all of them right there, the things we can do. I've got other videos on going more in depth on each of those, looking at the histogram, looking at the probability plot, the bar chart. Because why bar charts? Because bar charts are for categorical data. I guess I can be on the screen. Bar charts are categorical. Remember, Jesse first said right there, and great job, Jesse and Marcus right there. Jesse said this is quantitative, so we'd make a histogram over there, the blue quantitative one variable. It's not a bivariate display, which is in here. If you're doing bar charts, you're just doing one categorical variable. Since we're doing nearly normal, it's a quantitative variable. We don't use bar charts, we'd use histograms. So it relates to a lot of what we've been... I literally clicked the outro screen. That's on where the graphics button is. So I was trying to turn off the graphic right there. Decreasing the sample size will make the margin of error a smaller value. Okay. So sample size is what in these equations? Sample size is what in these equations? You got a 50-50 shot on this. Sample size is what in these equations? N. So let's just not even worry what the question says. Let's just look at this one right here. So you've got your equation right here. We're going to remove a little bit of the extra around all this. And the margin of error, we'll just delete down to make it nice and clean to see. The margin of error is this. Now, if you increase n, so if n gets bigger, now you're dividing by a larger number, margin of error would get wider. So this whole quantity here, if n gets bigger, like you make n a bigger and bigger number, the margin of error will get what? Because you're going to divide by a bigger and bigger number. You'll times those two together, it gets smaller. And think about this. When would you be more certain of your estimate of like making an interval? If you take a larger sample or a smaller sample, when would you have less uncertainty? Because margin of error is your amount of uncertainty. Like you go plus or minus a certain amount of uncertainty. So if you took a bigger sample, you'd be less uncertain, or if you took a smaller sample, you'd be less uncertain. So which of those? Reverse it, Marcus. Good answers, Marcus. You'd be less uncertain for larger samples. Does that make sense? Because if you have more data, you would have a smaller amount of uncertainty. So more data is when you have a bigger n right here. So, so you'd be less uncertain, which is smaller margin of error for larger samples. No worries. 100 points again, Marcus. Good practice right here. And so let's see if this says what we think it says. Decreasing the sample size will make the margin of error smaller. True or false? So with what we just learned in practice right there, they're inversely related. If you decrease it, it'll make it smaller. Is that inversely related? Is false. Marcus, great job right there. 95% confidence interval has this. It wants the margin of error. Now, a lot of people say to me with this, they say, how in the world do we get the margin of error on this? If we look at this and we say, well, what's the formula, right? Conceptually speaking, the margin of error is always what of the interval? Conceptually speaking, the margin of error is always what of the interval? I think it's a plus or minus. So if we go conceptual on this, the estimate would be here at the center. So that's where the estimate's at. So I'm using the same color coding. And then we go plus or minus. And that's the margin of error. So the margin of error is always what? Here's the interval. The margin of error is always what? So think about the plus or minus right here. Well, it's the distance from, that is correct right there, Marcus. It's the distance from the center. And we could find that. So we could actually, there's multiple ways to solve this problem. It's the distance from the center. So how could you, let's do it that way first. How could you get the center of this interval right here? How could you get the center of this interval? So 64 to 73.2, how could you get the center of that interval? The middle of that interval. How could you get the middle of it? So it's 64 and 73.2. Well, yeah. Well, and it's half the length of the interval too. Great job, Marcus, right there. And so we could, yeah, exactly. So we could get the middle of the interval too. I'm not used to the bigger calculator. There we go. Now we can do it right here. There we go. Look at that. Now you can see the history. Thank you for the people who suggested this. This probably will help people out. You could figure out the center of the interval by adding them up and dividing by 2. And so now that's the center of the interval right there, 68.6. And now the margin of error needs to be plus 48.6 or 4.6 or minus 4.6. And there is the other way that the margin of error is always half the length of the interval. So you could take the length of the interval, 73.2, and subtract from it 64, and then do half the length to confirm your answer. So the margin of error is half the length of the interval. And I like to do, we'll put this answer in, but I like for people to understand this such that they could solve problems without even thinking about it. Because if I tell you a steak dinner, I like to use this example right here. I just want a steak dinner. If I tell you a steak dinner costs somewhere between $40 to $60, how much would you estimate the steak dinner to cost? How much would you, Brian, estimate the steak dinner to cost what? It's a really good filet. This is a filet at a fine dining restaurant. Would you estimate it cost $10? I think I know what she solved for Marcus. 50, and then 100 points, everyone right here. 50, and then Marcus, you gave the what? So we'd estimate that it costs 50, and then Marcus, you gave the what, which was going to be my next question. Great job, Marcus, right there. And then, and you can check your work then to see if you get the values by using the margin of error and the estimate right there, because this is the estimate, and then this is the margin of error, plus or minus $10, and then you can double check. Yeah. Oh, and that is the margin of error, correct. The standard error is part of the calculation. The standard error times the confidence level, the T or Z used, is going to give you the margin of error right there. So it has 2 components. Hey, my mixer. And the success failure condition requires what? And so this is an easier one we've done a lot, so people usually know this one. The success failure condition requires what? At least 10 successes or no more than? What is it? At least 10. And if we don't meet the success failure condition, then we can't use the normal curve. This is an example where we don't have at least 10 successes. Great job, Elijah, right there. So notice how when you get more successes, you're noticing here on the bottom, the amount of successes is now 4, now 6, now 7, now 8, now 9, 9, 10. And as you go up and up in successes, it becomes more and more normal. But at some point, we basically have a curve that's good enough that the normal model can be used to describe the proportion. So once again, we want there to be at least 10 successes, at least 10 failures. If you talk to 60 people and you expect, let's say, sure, 5% of them to own cats, what is the expected number of successes? So if you talk to 60 people and you believe 5% own cats, what is the expected number of successes? You talk to 60 people and you expect 5% of people to own cats. 3, great job, Marcus. And look at that, not normal enough. And then the amount of failures would be 57, which you could check right here by doing the other one. That's NP naught or NQ naught, depending on which problem you're doing and how the problem works, the notation we use. But notice how this is not normal and the other one's not normal, just depending if you want to talk about the successes or failures. So we want there to be at least 10 successes, at least 10 failures. And if we have that, we are good. And this is used for categorical data, at least. There's at least. I'll click a wrong button every once in a while. Do we get that 10 out of 10? 10 out of 10. Let's do one more version of this right here. Always good to practice up and know what we're doing. Here we go with another version. Attempt 1, 8 out of 10. What? When did I do that? When did I do that? Okay. This way you get 2 tries. Which of the following is not required for testing means? So when we test means, we always, or the first 2 conditions are just like, well, what are the first 2 conditions we always use from now on? And the first 2 conditions will be random, we randomly collect the data, and 10%. So you've eliminated 2 answers. Boom. Oh, I remember when I did this last time, I got this one wrong. Mebot loving some randomness. And then how do we know to use success failure, or how do we know to use nearly normal? Like which one is used when what? This is the one I got wrong when we did it last time because I selected the one we do use, not the one we don't use. This is not required. But how do we know picking between this? It's either means or proportions, right? So if it's means, we use this. If it's proportions, we use this. So it says which is not a requirement. And we have some work from yesterday. This problem right here, if you take a look at the steps we were doing, this was a proportions test right here. Same thing works for confidence intervals. So you notice how we're testing P. Because we are testing P, you get down here and we're doing success failure. So it really starts at the very start of the problem where we decide we're doing categorical data. I've got the 4 different types of things we're doing up here, which will determine the conditions. And I want to mention this at this point. If you're wondering about the conditions, so Jesse, check out this video, and everyone else in the chat, check out this video too. But I have a really, really good playlist, and I need to send this out to everybody. But it's on the review page. And I want to post it because probably people are watching this video, I hope. Where is it? It's like 6 videos. It really goes over everything well. And I'm trying to think if it has things we don't need in it now. Okay, I'll find it. Give me 10 more seconds. I know I have it. I have so many playlists now. Not speedruns. Here it is. Test 3 concept review. This is one per. Okay. I should have done that in. Okay, so review help right here. So the reason I'm mentioning this, I'm going to pin this at the top, is because in my immaculate, perfect handwriting, sarcasm, I go over all the conditions right here. Condition 2 being 10%. As you can tell, there's random and 10% right there. Am I literally wearing the same shirt? I am. I love this shirt. It's so awesome. So with this right here, random, 10%, talk about the variable types. There's success failure. There's nearly normal. Checking for both distributions. There's the last one. That is funny. I know, right? It's one of my favorite shirts. And then there will be a 4th condition for the last 2 tests we do. But if you notice right here, nearly normal is used for t-test, quantitative, 1 sample t, 2 sample t. And then expected cell count is kind of like success failure, but it's for 2 categorical variables. So I'm using the color coding up here to show you that these are quantitative, hence nearly normal. These are categorical, but the chi-squared is 2 categorical. And we'll talk about what these conditions mean as we get to them. But nearly normal is always for 2 quantitative. Independent means literally means the 2 means are independent. I'm not even a Cardinals fan. I'm such a phony right there. But if you want, check out these videos. I go over all the notation. This was Winter Break 2019, I believe. So there it is right there. Yep, Winter Break 2019. I remember quite well. And I go over all the notation, every bit of notation. I swear there's not any errors. And I go through a test, basically using the hacks method that we use nowadays. But I decided to come up with an acronym to make it easier to remember rather than just like doing all these steps right here. And I state all the conclusions. And this is a long time ago. I reject the null that the true proportion of students. Yeah. Nowadays, the form I use is a little bit different. My p-value of this, which was less than alpha. Yeah. It's all the same stuff. I reject. I have evidence. So good stuff right there. Check out these videos. Very similar to how I teach it now. Still the same content. Gosh, 3.5 years ago. But these are the final things we'll be covering, and you kind of get a good walkthrough of a problem right here. Once again, some underviewed, 1,000 views. Not bad. 3-4 years ago. But if you're watching Office Hours now, please check out these videos. They're going to walk you through each of the chapters doing tests. Chapter 15, yeah, let's check that out here. After this one, you got it. We'll finish off this version of the quiz. And no matter what the shape of the parent population, as long as our sample size is 10, we're good. So this is the large enough n condition. So as long as your sample size is 10, large enough n is good. True or false? As long as your sample size is 10, large enough n is good. It's another way of phrasing this. So no matter the shape of the parent population, so we still use large enough n for nearly normal. So as long as your sample size is 10, no. If it's heavily skewed, you need closer to 100, so no. The parent population is where the data comes from, like the full data set. All individuals, skewed needs more, exactly. The only way to change the margin of error is to change the sample size. Rather than just saying yes or no to this, we should know another way to change the margin of error is to change the what here. So the margin of error, the plus or minus, can be changed by the sample size, but we could also change the what of the interval too. The estimate's not going to do anything to it. Well, to the margin of error. It's going to change the center of the interval. But another way to change the margin of error is to change the what. The level of what. What we are in the interval. Because the margin of error has two components. So another way to change the margin of error is what? We don't really impact the standard deviation because that is just the variation inherent in the data. So we don't control that. We can control how much data we collect. Like we could say, let's go collect more data. The T, which is the confidence level. Instead of saying like 90%, you could go to 95, and that'll make the margin of error bigger. Like when you go from 90 to 95 to 98, the interval gets bigger and bigger and bigger because think about the T has to get bigger. So when you use a T of like 95, it's close to 2. When you do a 99% confident or 99.7, it'd be closer to 3. T's and Z's are very similar. So the more confident you are, the bigger the T gets, like 68, 95, 99.7. So like a 68% confidence interval would be a T closer to 1. It does depend on how many degrees of freedom you have, but similar numbers, T's and Z's. The T is just the more exact calculation made by William Gossett, who worked at Guinness Beer, which could be the next question. This is false right here. We can change the level of confidence. Decreasing the sample size will make the margin of error smaller. False. A confidence interval is made from a what to estimate the truth about a what. So we think of the S word, we take what to estimate the truth for this. We say sample these. Oh, I just give one word away. Sample to estimate the truth for a population. Sample statistics estimate population parameters. And so a good thing to know exactly. And so when you make this interval right here, this Y bar is the sample estimate trying to understand the truth for what? The truth we are trying to understand right here, Jesse, is what? Like the thing in notation wise that we're trying to understand, like Y bar is an estimate of what? So Y bar is the sample mean. Y bar is our estimate of what in notation? Notation-wise, Y bar is the estimate of what? Or you could say it in words too, because I don't know what you mean by. So Y bar is the sample mean, but which mean? You are correct. So the sample mean estimates the true mean, right? So that's why when we interpret the interval, we're saying I am 95% confident the true mean, because the interval is an estimate of what the truth is. So the sample estimates what is true for all data. And yeah, great work right there, Jesse. Excellent job. And Jamarcus has the question on chapter 15. Which of the following hypothesis is not a perfect form? Yeah, let's do some hypothesis tests. Here we go. So I hope people got 100. Jesse, did you get that 100? You don't have to say if you don't want. People are always free to say or not say their grades. I like the hype of people getting hundreds. So you are always feel free to be like, yeah, I did, or you don't say anything, or say whatever you like. Sometimes at the end of class, people are like, got those hundreds. I'm like, woo! When does Pokemon Sleep come out again? July. We're moving. I want to buy something that's releasing as we move. Nice job, Jesse. Great work. Chapter 15. Which of the following hypothesis is not an appropriate form for an alternative? So the alternative is either less than, greater than, or not equal to. Less than, greater than, or not equal to. Those are the alternatives we use. The null always has the equal sign. Which of the following is not appropriate? Chapter 15 quiz. Oh, that's due tonight. Dun, dun, dun. Ah. So which of the following is not... Let's do... Here we'll do a bunch of Chapter 15 null and alternative questions. Great job, Jesse, right there. Excellent work. So when we do the alternative hypothesis, and I think it's page 30 that we have. We got so many Word documents open right now. I'm about to reach a new page of them. We pick between 3 different alternatives: the less than, the greater than, or the not equal to. Now, the reason we don't put, you think about if the null is true, then technically this includes it if we put a less than, not equal to. So we don't, because only the null can, literally, Jesse is talking the theory while I'm doing this. Jesse, 1,000 points, because you literally understood that right there too, because if we include the equal sign, and sometimes I've seen places do that, and it always irks me because it just doesn't make sense that we would include an equal sign in the alternative, because if we believe the alternative, well, then it contains the null. So you want these to be dichotomous. You don't want, they can't both be something you believe at the same time. So we don't include the equal sign down here. I swear I've seen some places do that, and I'm just like, why? It doesn't make sense. Then you could believe the null and the alternative at the same time. Like, you could have evidence for the alternative, which contains the null. So I don't like that. Maybe a statistician could argue against me, or any student could. But these are the 3 alternatives. We have less than, greater than, not equal to. These are called the one-sided here. So when you look right here, I have 1 next to this, and this is the two-sided alternative because it has 2 sides next to it. The one-sided alternatives also add up to 1 because you're going above a point and below a point. So if you add up the area, you'll get 1. The two-sided is always double the smallest because you're just reflecting this over to the other side when doing the two-sided alternatives. So you can find one p-value from just another p-value, knowing how the tests are done. Right here, it's important to note that this line is where I think TS is at. When you solve a test, you get a test statistic. In this instance, it'll be a Z. That Z right there is then plotted on the curve. We'll go to the end of this problem. And you notice right here, we got this Z statistic over there. We were talking about what it is. That Z statistic is all the way on the far side of the curve. And that p-value it turned out to be 0. Because what we saw in this data, we saw this result. That's what we saw. We saw 52% of their people getting their luggage back. We expected to see 86%. So that goes at the center of the curve as the most likely thing if the null is true. And then our result in a standardized format was all the way down here and was super unlikely by random chance. It's virtually impossible. The things that are more likely by random chance are towards the center of the curve. So you can see here, I'm trying to bring back my writing on it. The likely results, we lost that. So the likely results are at the center of the curve, but we landed nowhere near the likely results. So when you do your null and alternatives, null has the equal sign, alternative is less than, greater than, or not equal to. And there's other ones right here, so we can do other versions. Which of the following is the appropriate null? How can you instantly get this answer? Every time. If you see this, it says, which of these is the correct null? The null, da-da-da. The null has the equal sign. Marcus got right there. Boom. Freebie questions. We love those. Null has the equal sign. Boom. This one I like a lot. We did this during class yesterday too. Now, it asks you which one is the right null, but so I tricked people in class with this. Your friend thinks they're psychic, and so you're gonna hold up a card, and they're gonna guess the suit of the card. Now, there's 4 suits: spades, diamonds, clubs, and hearts. So the null has the equal sign, right? But if your friend is psychic, what is the alternative? And then let's try to say it as a sentence too. The null is that the proportion of time they'll be correct, the true proportion of time they'll be correct is 1/4, because by random chance, right? If they're not psychic, you don't believe them. And then Marcus automatically has right there. Marcus, let's throw Marcus 1,000 points. We're going a little crazy on these points today, but thank you for being here for office hours. Greater than, because they're trying to show you evidence that they're psychic, and then they should be better than the random chance. So if they're psychic, they should show evidence of that, which is the alternative-based claim. Now, this does ask the null So once again, null has the equal sign, easy question. This right here, it says, what is the null? Null is the equal sign, easy question. Man, those are easy ones. Now this gets a little bit more interesting. There are freebie parts to this. So the freebie parts to this is that the null has the equal sign. So if you're working on this question right here, the null has the equal sign. 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 Now, we're going to talk about how to get the answers for this, because when you're solving this out, at this point, we only have two things we're trying to understand. We are right now trying to understand either the true proportion or the true mean. How will we know the difference between the true proportion and the true mean? How will we pick between these two things right here? Like, why did I pick P down here? Notice how it's green. So why did I pick P down here instead of mu? And I'll start explaining this while people answer in the chat. This question was about people getting their luggage back, recovered luggage. So why did I pick P instead of mu? It's categorical. Great job, Jesse, right there. So this is categorical and this is quantitative. This is the difference. The next one over to the right is the difference between two quantitative variables and two quantitative groups, I should say. And boom, Jesse's got those notes. P is for categorical data. Mu is for quantitative means. And so we have to look at the question and ask, are they talking about P or are they talking about mu? So with this, let's see the first one. A casino wants to know if their slot machine really pays people out 3 out of 100 times. Great job, Jamarcus, right there. So if a casino slot machine is really paying people out 3 out of 100 times, now be careful. You need to pretend you're collecting data. You walk up and you watch someone get paid out at the casino machine. Next person doesn't get paid out. Is that P or mu? So for this problem right here, you're watching people get paid out. Okay, that person got paid out. That person didn't. It's P. A lot of people get confused because they say, well, this is numbers. But still, you're just collecting categorical. Did that person get paid out? Yes or no. So always go to the way the question's collected, and then you'll see it's the proportion of time people are getting paid out. Now, here's the thing. We now know the answer to all but one part. We'll come back to that here in a moment. So last year, customers spent on average, a little bit obvious right there. We're seeing if there's some change or whatever. Has it increased? So paid on average, P or mu. Last year's customers spent this on average. Has it increased from that? More on that in a moment. That is definitely... Which is... put the start of it, Jamarcus, and I'll try to find it here next. This one is Q, right? It's quantitative. So we'd go here and go to mu. And now don't pick the other ones. That is mean, mu, and mu. Whatever you put for here goes everywhere else. So notice, once again, look at the format. Once you decide this up here, it goes for both of these. The only thing that changes between the null and the alternative is the what. The only thing that changes when you write your null and alternative is the what. The only change down here when writing this is the what. And I've got it highlighted right there. The only change is the alternative has a different sign. Exactly. So a different sign has a different sign. That's the only thing that changes when we write it. So if you write your null, then you just change the sign for the alternative to what you're trying to investigate, what you're looking for evidence of. So next we have here a pharmaceutical company claims their new drug has a cure rate of 30%. Cure rate from reported by Psia has a new drug has a different. So cure rate would be for the given situations. I might actually take out my contacts. Now my left eye. Man, I hate my contacts. Yeah, we'll check that out here in a moment, Jamarcus. So the cure rate is going to be the proportion of people who are cured. We wouldn't use p hat because that's the sample. We know what the sample is if we watch the sample. And so P, and after this question, I might take out my contacts. And then a bank wants to know if the percent of customers using their website has changed. So people using the website is proportions. And then here's the thing. It's always the researcher's question that determines the sign of the alternative. So the sign of the alternative is going to be based on the question itself. And if the question doesn't indicate a direction, there's a keynote to have, you should pick the what alternative. If the question doesn't indicate a direction, you should pick a what alternative. If the question doesn't indicate a direction, you should pick the what alternative, the not equals. So if it doesn't indicate a direction, you pick the does not equals. So in this one, it says, does it really pay out 3 out of 100 times? Well, it either pays out that amount or it doesn't pay out that amount, so it's not equal to it. They're trying to see here, has it increased from that amount? So is the true mean greater than that amount? They're trying to see right here if it's different. So this one does tell us quite clearly. They're seeing if it's not equal to. Now here we go. Has it has changed wants to know if the percent of customers has changed. Notice how when you highlight the text, you can see what they're doing right here because they'll change like has decreased, has increased, has changed, is not equal to. So once again, they have the ability to kind of change what the question is when you're working on it. For each of the given situations, define the parameter. Yeah, okay, let's see if we can find that one. Wait, but that was yeah, here it is. So this is sort of the same thing. So what is the first thing we know right here, Jamarcus, about the null? The first thing we know about the null is always what? What do we know about the null always, every time? So what do we know about the null every single time? The null has the what? The null has the what? We can do this right here with this one. We can be like, the null has the what? Every single time. The null has the what? Well, the null doesn't have the p. So sometimes there's a p in the null, but the null always has the what? The equal sign. The null always has the equal sign. So when you're writing your null hypothesis, it's that something you want to understand is equal to a certain amount. Great job, Janie, right there, and good job, Jamarcus, too. The null has the equal sign. So that makes one of these sets of blanks pretty easy, that we always just put the equals here for the null. Once again, don't look through their answers. Try to figure out the answers yourself before looking through what they give you. That way you're remembering how to do it and not just kind of scanning through the answers. Because then you'll be like, okay, the null has the equal sign, so we say something is equal to something else. Now it comes into play, are we doing p or mu? So Jamarcus, when do we use p? When do we use p? P is the true what? So when would we use it? P is the true what? So when do we use it? What does P mean? Now, it's not p-value. P-value is a different idea. It's probability. P is kind of, when we just use P, it is probability sorts. What is P and when do we use it? What is it? There are 100 points right here. What is P and when do we use it? P stands for what? 100 points. Any guess? So make sure to proportion. Great job, Janie, right there. We'll throw Janie some 500 points. And we use it when it's categorical data, right? P and more specifically, though, to be exact, proportion, true proportion. So it's the truth. So that's why we wouldn't use p hat, because that's the sample proportion. We're making a statement in the null about what we believe is true for all the data. So we'd say the true proportion is equal to something. So what if mu is mean, it's actually what used for quantitative data. Good to see you here, Sam. So mu is mean, but it's not just mean, and we won't use mean right here, but mu is not just mean, it's the what mean. So mu, just like proportion, is true proportion here with p instead of p hat, which is sample proportion. Mu stands for what? Not just mean. It is mean, it is the mean, but it's the what mean of the what, if you want to get specific. I had teachers who made me say that. Mu is the what mean. I had a teacher, I was like, it's just the mean. He's like, no, you have to say it's the blank mean of the blank. So what is mu? And it's used for quantitative data like height, weight, GPA. Those all have a mu. Kinda. Good answers just right there. I guess so. Let's go crazy. Are you ready? The true mean of the population used for quantitative variables. Does that make sense? So that's like the in-depth understanding. The true mean of the population used for quantitative variables. So as long as you understand what's going on with it, but that is different from y bar. Why? Because y bar, I'll do that in a different color right here. Why is y bar and mu not the same thing? Y bar is the sample mean, which is for a sample set of data, and p hat is for the sample proportion. So just understanding the differences right there, like y bar is the sample mean, mu is the true mean, p hat is the sample proportion, p is the true proportion. So, and then this one right here would be y bar 1 minus y bar 2 is the estimate of the sample difference. So some good understandings of what we're doing and the notation on how we use it. So the first thing to understand with this question is, are we doing P or mu? Seatbelt compliance was this. So you're asking, are people wearing their seatbelts? P or mu? So are people wearing their seatbelts? P or mu? And then you'd figure out the this of people wearing their seatbelts. And then think if it makes sense if you say proportion or mean. P, yep. So wearing your seatbelt's a yes, no, and then we'd have the proportion of people wearing their seatbelt. So once again, don't look at their answers, just understand it's P because it's the true proportion of people wearing their seatbelts. Last year, a survey found that 59% of employees were willing to pay for on-site daycare. Will you pay for on-site daycare? That's what they were asking them, P or mu. So will you pay for on-site daycare? They're interested in the mean of paying of online daycare or the proportion of online daycare. They didn't quite say the full sentence because it'll give it away if I say it in perfect context. P. They wanted the proportion of their employees who will pay for on-site daycare. So that's P right here. We're just focusing on, is it P or mu right now as we write this? Because that's more traditionally what you would do. You'd write out your null and then just change the sign for the alternative. Regular credit card customers have a default rate of 5.8%. So they're figuring out if people are defaulting. So P or mu. Like, did you default? That gives it away. When you think about collecting the data right here, like, okay, we're looking to see if people defaulted. Don't worry about getting it wrong. This just becomes like, as you think about like, how are they collecting the data? You start to just get these down right here and learn how to do them. And Savannah, good guess. 500 points, Savannah, right there. We throw points here. So are you looking for the proportion of people who default, or are you looking for the mean of people who default? So think about saying it that way. Can I check today's end? Yeah. Sam, let's do it here in a moment. Nate, nice job, Savannah, right there. The proportion of people who default, right? So when you collect data, you would say, did that person default? And you find out the proportion of people who defaulted. So this one is also P. They might all be P for all we know. Let's find out. Last one might be a 2. Regular credit card customers have been with the company on average for 15.8 months. You would collect this data by saying, how long have you been with the company? P or mu? Last one is mu. Great job, Savannah. Right, they're only throwing 100 points for right answers. So you got that 500 for the other one right there. Savannah, great job following along. And a lot of people say, well, how do I know the difference between P or mu? This is a good question right here to practice. Now, the only thing that changes, just say it one more time. I know we've been saying this a lot. It's just memorization. The only thing that changes between the null and the alternative is the what. 4-letter word starts with an S right there, ends with an N. 4-letter word. The only thing that changes between the null and the alternative is the what. So we have the population parameter, the thing we hypothesize it to be. The null has the equal sign, and the only thing that changes between the null and the alternative is the what. Thing that we should always know when writing this out, because we wrote ours out here just like that. Data analytics 7? Yeah, I talked about that, Taylor. You got it. The only thing that changes between the null and the alternative when we write it out is the what. And this indicates the way we shade, which is very important. So here we'll look at another one real quick down here. When we're doing this, the does not equals indicates that we will shade both sides here at the end. Hence, the p-value is over here. So the only thing that changes between the null and the alternative is the sign. So we have here, they want to know if it's increased. So that's going to be greater than. They want to know if it's decreased. That's going to be less than. They want to know if it's lower. So you see here, they want to know if the rate's lower. So that's going to be less than. They want to know, bank wants to know if their customers have been with the company on average the same amount. So they want to know if it's the same. So the same doesn't indicate a direction. The same is like, is it the same or were you not the same after that? Ben Folds song. So there we go. Really good question. Good practice knowing how to write those out. Can also do quiz 16. Yeah, a statistics professor. What? Look at how much we've done of this already. And then we'll do some more right here. On a higher textbook costs, that's the claim. So that's the alternative. Students want to test to see if they run a mile time or different after a new training regimen. In a criminal jury, when someone says not guilty, what is the bad word we don't say in our class? And then I think we're going to switch after like 2 more. We'll have almost done half the questions right here. We're going to go a few more minutes on this, and then we'll switch over. So what is the bad word we don't say in our class? What is that bad word we don't say? We don't say accept right there. Do not say accept the null. We either reject or don't reject. So if you're watching this right now, think about this. If your parents say, did you pick up the dog today? Like the dog was at doggy daycare. Did you pick it up? You say, I failed to pick up the dog. What are you telling your parents when you say, I failed to pick up the dog? Your parents are home and they're like, did you pick up the dog? And you say, oh, I failed to pick up the dog. Your parents will understand that. They'll know what you're talking about. Failed to means you what? You did not. So I failed to do that. Well, you did not do that. So you either do something or you do not. Do or do not. There is no other choice. I don't know the correct phrase. So reject or not reject. I like to say not reject the null right here. We don't accept the null. That kind of means is like that's what people think of when you say I accept it as true. We don't say that. So if we start a criminal trial and we believe someone is not guilty and then we end with not guilty, well, then we continued, or sometimes people say retained the null. Good question, Jamarcus, right there. So we retained the null. Retain means to not reject. So you'll hear different phrasings in different disciplines. The probability of seeing sample data like the ones we saw, that's a p-value. Probability of our results or results from our stream, with more detail on that. And reject null hypothesis. Reject null hypothesis, the p-value is, ooh. Finish the phrase, don't click the sentence. We should know this one very clearly. I've had people ask this in upper level classes. Look, it's like that bar's right there. When the p-value's blanker than blank, reject the null. We'll end with this one, and we'll have done half the quiz in no time at all. Yeah! This is what Taylor wants too. Good question, Caitlin, right here. Let's do that here next. 2 people have asked for that one, and then we'll do more. Yeah, let's do data analytics 7. So the key phrase we need to know is reject the null when the p-value is what? Or you could go in more depth. This is something you should have memorized. Thank you, right there. Oh, wow. Jesse, thank you so much. We're going to do data analytics 7 next. Reject the null when what? This is a phrase you should have memorized and know very clearly. Don't click their answers. So don't worry about what their answer is. Know this phrase. The way to think about it, we'll draw it visual here while people think it over, is you have a bar. The bar is usually set to 0.05. And this is your rejection region. And this is your not reject region. We'll do different colors. And when you get your p-value, the p-value will either be here or here. So we reject the null when what? We reject the null when what? Got some animations now. We reject the null when what? Don't worry about their answers. Understand when we reject the null. We could go more in depth what it means, but just by virtue of memorization for this point, reject the null when the p-value is what? Technically, the not reject region would be at or above. Reject the null when what? When do we reject the null? Give it a moment more here. Reject the null when what? Like, how much detail could you give me on the explanation? This is a huge concept, hence why I'm pausing on it, which we should. Sometimes people say, when do we reject the null? And I say, we got to know that. Reject the null when? It means your results are unlikely by random chance given the null is true, which means unlikely, statistically significant, a lot of words we use. So we reject the null when the p-value is low, reject the null. Great job, Jesse, right there. And low means lower than 0.05, which is the assumed rate of alpha, which is our type 1 error rate. When the p-value is high, just let it fly. Great job, Jesse. When the p-value is low, reject the null. When the p-value is high, just let it fly. And low means lower than alpha. When the p-value is lower than alpha, which is assumed to be 0.05 unless otherwise stated by the problem, we reject the null hypothesis. If the p-value is high, we just let the null fly, equals, which means not reject. So, yeah, exactly. When the alpha level the researcher states. So someone could say, I'm using this alpha level, and so someone could change it and put an alpha level of this, and now we have a lower alpha level, which means we have also lowered the what, Jesse? One more for 500 points. We've also lowered our what for this problem. So we've also lowered our what? Ooh, this is an advanced question. So We did lower alpha. That is, by lowering alpha, we lower alpha, but alpha is also what? Like alpha is literally your type what. So we lowered alpha, so you'll have less what's now. You'll have less what's by lowering alpha. Type 1 errors, yep. But now you'll have more what's because these are inversely related. By having less type 1 errors, you'll now have more what's. Do I have that in the slides still? I don't know if I have my drawing of it still. We're going to switch topics. So it's chapter 16. I think I drew it. No, then I have it on a worksheet still if I didn't close down. By lowering alpha, I think I reset the computer since then. Hey, there it is right there. So if you lower alpha, so this would be lower, you'll have more type 2. Yeah, type 1 and type 2 are inversely related. You'll also decrease the power of the test. So type 1 and type 2 are inversely related, but type 1 and power are positively related. So if you lower type 1, you would lower power, but you would increase type 2, which, I mean, overall, well, you'd have less type 1 error. That's good. Both errors are bad. Just depends on context which error is worse. So I need to say that in class too, because sometimes we've thrown that sort of question. So we've completed half of the MyPearson very quickly. Reject the null if the p-value is small. That's such a... They could have given so much more detail that the p-value is lower than the alpha level decided by the researcher. Yeah, that could have had way more detail on it than small enough. Reject the null when the p-value is low. Okay, let's go over and do some... I'm so bummed out about the less than thorough answer MyPearson gave right there. Let's do data analytics. I was like, what is this answer? Oh, it's like just p-value low, reject the null. Well, that's how I teach it, so you get that answer right very quickly. Data analytics. Let's go to some data analytics. Number 7. Due on Wednesday next week. It is Wednesday next week, right? I think so. Okay. So let's go do it. Let me take the note here of where we're at. Data analytics number 7. Stat tool 1. Data analytics. 7. Okay. So when we do confidence intervals, there we go. Now I hear myself a little bit better. Should turn down this to play audio in my ears every day now. We will be assuming, you will assume this passes, you'll assume your sample passes the randomization condition and 10% condition. Good. Always good right there. Assume we pass stuff. So we are using this bike data right here. I actually have this over here. Let's open it up. Have it over here in R also. That's where we got it from. Ooh, I don't like the way those columns look. We got an identifier. We got the demand for the bikes. We got the day of the week it occurred on. We have whether it's a working day or not a working day. We have whether it's a holiday. We have the weather. We have the average temp, the effective average temp, the average humidity, the average wind speed, and I'm trying to remember the last one right here. I should know this, but I remember by now. There we go. Temp. Variable? Effective average temp. Oh, Fahrenheit. Oh, Terry added some stuff here to this. Yeah, I was like, I don't know these variables. Okay, so let's look at the questions and what we have for this. Confidence interval for the proportion. Confidence interval for the mean. So we're just really creating 2 confidence intervals. How do you know if you're going to get your points? To check to see if you're going to get your points, always go to the rubric. So always go to the rubric, look over the rubric. Name included. Name included is important. Put your name at the top of the document. So top left corner of your document, your name. Make sure it's there. You get that half point. Random sample. So we'll talk about how to take a random sample here in a moment, but make sure you take your random sample to start. That's a half point. So these should be free 1-pointers right there. Let's talk about how to take that random sample. To take a random sample, go here and go to tables, subset, and then we are taking a random sample of how many? They both use the same random sample today. They should. 300 plus the last 2 of your UTID. So when you go to tables subset, you'll go right here, type in 300 plus the last 2 of your UTID. Make sure it's the last 2, whatever it is. And so you type in the last 2 of your UTID. And after doing that, 300 plus the last 2, whatever it is. You could have 0, 0. You could, because that could be the last 2 of your UTID. Click OK. It'll actually select it, and you know you've done it properly if you see down there 300 plus the last 2 of your UTID. Now, I'm not going to do the data. I'm not going to use this data to analyze the confidence interval for the proportion and the confidence interval for the mean, because I don't want to do your exact assignment, but the similarities between what I do and what you're doing is very consistent. And taking a random sample is always the same way, no matter if I use a data set like this, table, subset, and we go right here, and we take a random sample of something like that, and then there's our random sample. Just make sure it says it, and I'll probably be using this data set from now on because I don't want to use the exact same data that you're working with. I always hate when those columns wrap. Okay, so now let's take a look over here. The question also says next, we'll just go by the rubric. The first thing the rubric says is confidence interval of a proportion jump output. The appropriate analysis was performed and correct screenshots are provided. This is only worth half a point right here, but let's take a look about how to make a proportion confidence interval. So in jump, we have red for categorical and blue for quantitative. So if we're doing the confidence interval for proportions, it needs to be categorical. Now make sure to do the variables it tells you to do. So you'll be selecting whatever variable it tells you. And when we look here, like if we want to know the proportion of people who are male from the truth for UT, we'd select that column. Kind of makes it a little bit easier if we do that. So you can select the column there and go to Analyze Distribution. So we're going to analyze the distribution of gender right here with the interest on the percent or proportion of individuals who are male. Remember, it's proportion because it's categorical, and jump tells you that with the red color right there. Now you can double click it. If you've selected the column, you can drag and drop, or you can just click Y columns. No matter what you're doing, just make sure it ends up over here in this field and you've done it correctly, whether you drag and drop, click, or double click. So now we're going to click OK, and here we are. We need to get this into horizontal layout. Click the top red arrow. We'll zoom in a little bit here. Bring it towards the center of the screen. Click the top red arrow and then click stack. That'll put it in horizontal layout for us right there. Next, we're going to click the red arrow right here and go to histogram options and go to count axis. That's the second red arrow, histogram options, count axis. That'll allow to count axis. I'm also going to make this a little bit nicer size-wise. And then we're going to click the second red arrow again, histogram options. And I like to go to histogram color. It's off the screen a little bit here, so whoops, wrong button. And then I'm going to change the color. You don't have to, but I like a nice purple right there. Good stuff. So we've got our good looking histogram right here, which has everything we need, but now we need to add in the confidence intervals. To add in the confidence intervals, we click the second button again, and we go to confidence interval, and we specify whatever confidence we're told. You're given by default 90, 95, 99, and then you have other right here. The other allows you to enter in any value you want, like 91.2, whatever you want. You can just enter in ridiculous values, but we're going to enter in, for this point, a 90% confidence intervals. And I want to say this, I'm going to wave my hands in the air. Make sure, I know nice, right? Nice and easy, and make sure when you're doing this, you look at the instructions and you see whatever percent confidence it tells you to input. So if it says 90, 95, 98, 99, put that in. Put whatever it says there for the percent confidence you're doing. This is just how to make proportion intervals right here, nice and easy. And there's the proportionate interval. And make sure when you look at this, it says the percent confidence right here, which is actually 1 minus alpha. This is similar to doing an alpha of 0.10 on a two-tailed test, which is another concept we should know. So that is the confidence level and can be found 1 minus alpha. So when I take screenshots of this, I like to take my screenshots as follows. I go here for the first part. There's my screenshot. And I go right here. Screenshot this. Bring it over to my Word document. Drop it in right there. Make it a little bit smaller. That's quite large right there. There we go. Center it up. Click over here on picture format and give it a nice, nice little background like that. Good right there. Or this one's also classic. Little bit of pop to the picture right there. Whatever you like. It's your choice. Make it look nice. And now we go over here and we grab the second portion of the output and we have the following output right here. And we don't need that note. We don't need that. We're going to take this. And if you do get extra, like let's say I really don't like that little extra bit right there, click picture, go to crop, and bring in the little black bars right there till you remove the extra you don't like. And now you have your perfect little screenshot that you want right there. And then we're going to take this, decrease the size down a little bit. Then we'll throw on a little background right there. Good stuff. Well, we want to keep them similar. I don't like that now. I'm very particular on my stuff. Oh, you see now because of the crop. Okay, we'll go with this right here. There we go. Got to be exact. Okay. I don't like the shadows now. See, it's cutting the text, so watch out if you do that. Oh, that's great. That's good. I like that. That's great. That's there we go. Perfect. Looks great. Love it. And you can do some fine tuning on this stuff, but that looks really nice. Good borders around them. There we go. Got some space. So once again, we should know what we're seeing right here. We have a histogram showing us the count of the observations of individuals who are male and female. There was 165 males and females in the survey. There were 156 males in the survey. 51.4% of people were female. 48.6%, rounding right there, were male out of the 321 people. There were 2 levels. There's no missing data. And you can see the counts of the observations right here. This is categorical data. So now we look at the following information. Now, this looks like a lot, but what is it trying to tell us? And this is where we go to our interpretations. We interpret it as, I am blank % confident that the true blank is contained in the interval blank to blank. So here's the thing. What part of this do you think people usually get wrong on the test? What part of this do you think people usually get wrong on the test? Where do people make mistakes interpreting this interval? When they write their interpretations, all the mistakes usually happen right in here. But here's the trick to it. You will always need to give the middle exactly. You'll always need to give the context, but you'll pick between 3 things. You'll either be talking about the true proportion, the true mean, or true difference between means. So what are we talking about here? I am 90% confident that the what? I am 90% confident that the what? What is the thing we're trying to understand? The true what of what? I am 90% confident that the true what of what? So we've got parts of it highlighted right here to help us interpret it. I am 90% confident that the true what of what? What are we trying to interpret? Are we trying to interpret the true proportion, true mean, or the true difference between means? And remember, this one is having us do a certain one right here. Categorical data will lead to this. I am 90% confident the true proportion of males, is contained in the interval. And then for the end of it, we just give the lower bound and we give the upper bound. I am 90% confident the true proportion of males at the University of Tennessee is contained in the interval 44.04 to 53.17%. You can do percent or decimal. You just put those numbers in, that is proportion. So yeah, you might want to just keep it as a decimal when interpreting it. But that is going to be the interpretation right here. Remember, we won't use all these words. We're going to look at the data to understand what it is and how to interpret it. You just can't do both. Oh, yeah, I wouldn't do both. Great answers, Jesse, right there. Yeah, exactly. I would not do both of them. And so now, conditions for a confidence interval of proportion provide all the conditions needed for the analysis. Okay. All three conditions are listed thoroughly. Explanation why or why not the condition passes or fails. So when we look at this right here, what are the three conditions? Random. We've taken, so I'm not going to write this out, but I'll talk about it. Random means we take a random sample of the data. So you need to make sure you've taken a random sample and provide reasoning that this was a random sample. I think you should be able to provide that. 10% means less than 10% of the population was sampled. So provide a reasoning that less than 10% of the population was sampled. So make sure to explain that. And then before we get to this, and this is not a condition, but we always pause because the third condition depends on the data we are doing. And I posted a video right here. So let me open this in a new link. This is a video. It's pinned comment right now where I go over the conditions and I explain that we pause here because the third condition is different. Great job with the pause in the chat. Same shirt right there in the past. So the third condition depends on the type of data, and we're doing proportions. So it's the success failure condition, which states we need at least 10 successes and we need at least 10 failures. Now, what's really good about this data and seeing it in JUMP, how many successes were there and how many failures were there? So how many successes were there and how many failures were there? So if you want, you can solve NP hat and get the amount, or if you know what you're looking for, you can see it. So here's N, and there's P hat, and then there's Q hat. So here, watch. I'll solve NP hat, but does anyone know what NP hat is before I solve it? So getting used to this right here. Clear the memory. Okay, so N is 321, NP hat. Yeah, there it is right there. There it is, and it just didn't carry enough decimals. That is it right there. That is NP hat because that is X. Remember, X over N is P hat, so you can work the equation to get 156. And then you could say there's 156 males and 165 females. So we have at least 10 successes and at least 10 failures. So yeah, that is, I mean, I would say the success failure condition right here after we pause. Don't write down pause. Viewers might be wondering what's going on. Success failure condition. And we definitely have at least 10 successes, at least 10 failures. But here's the thing. You should quote the numbers to really make sure you're going to get the points here. Quote the numbers. Like talk about how many successes there were. Well, that's successes, that's failures. So that is the amounts, and know what you're seeing right here. P hat is the thing we're interested in understanding from the sample. This is the complement, and then N is the amount of sample size. So in notation, this is X right there. This would be N minus X. So that's all the notation for this problem that we have written out right there. And then the confidence interval also gives additional information. What else does it ask us to do? And we'll do a little cleanup on this, make sure we have everything. Where'd it go? It's over here, I think. Confidence interval interpretation. So we interpreted the interval. Good to see you here, Jack. And confidence interval for the mean. So now we're doing confidence interval for the mean. Let me mark that first part of the video as confidence interval for the proportion and data analytics proportion interval. So this is going to be the mean interval. Stat 201, data analytics 7, mean interval. And so let's take a look at the mean interval right here. The appropriate analysis was performed and correct screenshots were provided. So when you are doing this, if you're watching this part of this video, what do you need to make sure you have? You need your what when doing it. I'll pause right here. Someone might answer in the chat. If you are creating a confidence interval for the mean for this assignment, make sure you've used your random sample. Make sure you have your random sample. You'll know right there if you see rows are 300 plus the last two of your UTID, you're using your random sample. You will be using a quantitative variable like something like GPA. So GPA right here is a quantitative variable, and we're going to go to Analyze Distribution. Now make sure to follow the assignment. I'm using a totally different data set, so you won't have GPA for your variable. Analyze Distribution. If you've clicked the variable, you can just click Y columns, or you can double click the variable, or you can drag and drop. Make sure to put the variable you're interested in under the Y columns over there, and make sure it's the correct variable. It'll be blue if you're analyzing means. That's how JUMP tells you the variable is quantitative. So we're going to go ahead and click OK right here. Now we see the histogram and the summary statistics along with the quantiles and the data. The next thing we want to do is put it into horizontal layout by clicking the top right arrow and clicking stack. Hey, Tyler, good to see you here. This is going to put it in horizontal layout for us. Boop. There's horizontal layout. I do like to make the histogram look a little bit nicer, take up a little bit more space right there. There we go. Now, if it says make a 95% confidence interval, you already have a 95% confidence interval right here. So the 95% confidence interval is provided. We can make other intervals very quickly, though. We'll talk about that here in a second. Let's go here to the red arrow. We're going to go to histogram options and go to count access right there. I'll pause so you can follow along. So the second red arrow, make sure you're on the second one, histogram options, count access. Now go over here again, and if you want to change the color like I always do, histogram color and a nice light purple right there. Yay! So we now have the histogram with the cool color, and we've got a count access on it, and we have the quantiles and the summary statistics. We already have a 95% confidence interval for the mean. But let's say you're not making a 95% confidence interval for the mean. Let's say you want some sort of other confidence interval. Well, going over here to the second red arrow again, you can go to confidence interval and go to any value you want by going to other. Other just allows you to put in some sort of value you want, like 98% confidence. We do the two-sided, and we don't say that we know sigma. That would be a Z interval. So you could do other things. There's lots of options in jump. Let's go ahead and click OK right here. And now that we click OK, we get all the output we need. Now, here's what you don't want to do. You don't want to try to take a screenshot of everything on the screen at one time. Think about what the reader would see. So this is a little bit larger of a screenshot, but you can do it. We're going to go ahead and take this right here. If you take a little extra, no big deal. And now we've got our screenshot right here. Good. We're going to go back over here to our document and drop this in. And we're going to throw a little border on this. Let's go shrink it down a tiny bit. Throw a border on it. And I think that looks pretty good right there. Make sure it's clear, easy to read. Should be a good, nice, clean screenshot with no extra. Just take a look at how all the screenshots, I know I've written on them, but they don't have extra, and it looks like the border really helped kind of make it look great. So there we go. Make sure your number line's visible. I got kind of lucky, very close on that. Now we go back here. We take our confidence interval, which will be our next screenshot, and let's go ahead and grab this. We're going to go right, take a little extra. There we go. And now we're going to go here. That's very large. I know. I found the border. It's all about presentation. I'm going to try to make it similar-esque in size. This is just way too big. Try to think about how the sizing would look. If I'm going to do some professional report. Yeah, this is, Isabella, this is what we're doing right here. This is Data Analytics 7. Yep. And now we're going to throw in a border. Thank you so much, Isabella. That's already 100 points right there. Ooh, we don't throw that border on there. That's ridiculous. There we go right there. Who uses that border? Good border right there. Not a big deal. We have that little extra. You're welcome. And I do like to center these. I think it just looks nicer as a centered graphic on the center of the screen. So we now have our histogram with the quantiles, with the summary statistics. We have the confidence interval with the lower and the upper bound. We have the level of confidence. Make sure to use what was appropriate for the assignment, because I am talking in a bit of generalities right here, because I want you to go in and look at what confidence level you need. If you don't use borders, they shouldn't. You'll get counted off if you could possibly get counted off, because I think there's a neatness. Let's go look at the rubric again. I think there is neatness. Write up. They could do something with screenshots related. Like, there's no neatness on this one. There should be always. But if you do like really crazy large screenshots, then, we want it to look professional, which is key. So I guess you wouldn't. The appropriate analysis was performed in correct screenshots. And this is the proportion interval. Conditions for the interval are met. So how many conditions do we basically have that we just go, what are our two conditions that we know that we just instantaneously rattle off really quickly? The two conditions are always what? No matter if we're doing proportions, means, two means, or chi-squared, which we'll get to, the conditions that we do really quickly are, did we randomly collect the data? So make sure to explain that to the reader. Is it less than 10% of the total population? And so I think I show the arrows here in a moment. I'm like, those are for every type of test. There we go. That's where I show it's like for all the tests. And then we have to pick the third condition. We like to say pause before the third condition. but now we're doing means. And if we're doing means, it's because it's a quantitative variable. And we will have the 2-sample t-test next week if you're in my class. And so with means, we talk about Mr. T, and we have the nearly normal, which means we need to look at the shape of the data. So you notice here I drew some shapes. If you're doing the 2-sample t, you'll look at the shape of both of the distributions to compare the means of both the distributions. That's why it's a 2-sample t. There's 2 groups of data, and we're going to look at the difference between the means. Good to see you, Amel. I'm totally mispronouncing. Please correct me if I mispronounce anyone's name. Amelie right there. Please correct me if I mispronounce anyone's names. And so with this, we need to think about the conditions. Random. Did we randomly collect the data? 10%. Is it less than 10% of the total population? And last but not least, nearly normal. Now, here's the thing. This data is a bit skewed. There are outliers down here, but the sample size is rather large. So this is where the central limit theorem comes into play. Remember, the central limit theorem states, so let's go to central limit theorem applet. The central limit theorem states that the distribution of the mean... Whoa, what is this? Did they just change that? Here it is. That was a totally different applet. So here we go. If our distribution is skewed like this with some outliers down there, and then we've got data over here, the distribution of the mean will be more normal and tighter for a sample size of a very large amount. So we could say, you know, talk about our sample size. Our sample size is very large, and the distribution of the mean will probably land in here somewhere, maybe over here-ish. There we go. And look at that. It's more normal and tighter, but notice how this still has some skew. We would need a much larger sample size, like something like 321 is quite large, which would counterbalance that. And I even did maybe even a little more skew than we have. So that's the important things to understand with nearly normal is we have 4 ways of checking it. We can look at the histogram. We can do a normal quantile plot, normal probability plot, a goodness of fit test, or we can talk about the large enough n condition, which states if the sample size is large enough, then the distribution of the mean will be nearly normal. And we need to have a good estimate of the shape of where the data came from. 321 is a good estimate of the shape of the parent population, that there's some skew to this in outliers. So I would say it's nearly normal for the distribution of the mean. The data itself is not nearly normal, but we're trying to understand the distribution of the mean. I think that's where people get confused. We're not interested in this data, which is how I drew our data. We're interested in the distribution of the means of sample size 321. I know that says 25, but the thing doesn't let you go up to 321 sample size. So is the distribution of means of sample size 321 normal? Probably good evidence to believe that via the central limit theorem, large enough n. And just make sure to explain that right there. And so with that, we would pass all the conditions. Make sure yours passes. Next, let's look at the conditions right here. Or that's all the conditions. So now we need to interpret our interval. Oh, we got this. So here's where, and I want to pause. I'm going to give 1,000 points if anyone gets this. I'm going to see if it lets me copy all this. Perfect. How would we interpret this interval? And I don't think that this one is one we should be able to do for the test. So I'm going to highlight the portions. So if you're watching this video now, pretend this is the test. And pretend this is the test. I'm giving some hints. I am basically doing it for you right here by showing where it is in the output. 1,000 points in the chat. There it is. There's all the color coding and highlighting with the context, with what we're talking about, with the lower and the upper of the interval. Those are the 4 components. If you're wondering when it says the 4 components right there, it's talking about component 1, component 2, component 3, component 4. And so component 1 is going to be this right here, the level of confidence. Component 2 is going to be the context, which is the harder part for a lot of people. So there's component 2. It's not the histogram, but I mean, that is the data. Component 3 is the lower. And there's the upper right there. So let's see here. Just filling this out is a lot of times hard for people, but usually the confidence level and also the lower and the upper is the easier part. So you just talk about how confident you are that the something you're trying to estimate, the true this, is contained in the interval blank to blank. So this, we'll give it a moment more. Put a little chill music on, but this is going to be... So see if you get the same answer I do if you're practicing for the test, because you will write these out. I am 98% confident that the true mean GPA for UT students is... Great job, Jesse. That's it. And 1,000 points right there. Great job, Jesse, because that is when Yeah, true mean GPA of the students or whatever. Like if you're worried, just give it a little context on the test, and if the graders are mean, just let me know. I am 98% confident the true mean GPA of students contained in the interval blank to blank, 3.11 to 3.26. Yep, right in 2 decimals is probably fine right there. Totally prove it, because GPA usually reports like 2 decimals. If you go to you could go to 3. If you go to 4, then people are like, think about it, only Mr. T is mean. Exactly. And so this is a T interval. This is an interval for the mean. So you could do the formula yourself, and let's do a quick review of that. If you wanted to do the formula yourself, you'd have to know the notation, and the notation here is that this is y bar, this is s, this is the standard error of the mean, this is the lower, this is the upper of the interval, this is the sample size. So the formula would be 3.1845, which is y bar plus or minus And let me ask this. Why do you think I basically know the T? That's the T star with n minus 1 degrees of freedom. How did I know the T right there, Jesse, when... Oh, no, that... Wow, I'm reversing where things go. How do I know the T star? Look at the degrees of freedom is the answer. So the degrees of freedom are... Degrees of freedom are large, yep. So the T is now basically the Z. Since I've memorized so many Z's, I know the T is basically this. So I know a good estimate of the T, and then the standard error right here, S over square root of N, which is the standard error. My gosh. S over square root of N. And so these are things you don't have to do, but good to know, like what you're doing with the formulas. So this is the margin of error right here. And that should be about 0.066. So 2.33 times 0.0337. There's right there. Is that right? Ooh, what have I done? 98% confidence. Standard error 0.0337. Have I done an error in my math? Oh, that's the 95. Oh my gosh. Look down here. Look at that. That was the 95. That was the 95. So I should have used, if I was like checking this one, that'd be 1.96. I was like, why are the numbers not working out? There's the number right there that I found. So I was like, wait a minute. Why are the numbers not working out? There's the number I calculated. They're going to carry more decimals and be more exact, but I got it to 3 decimal places because I could estimate the T right there. If you're wondering how to get the T to exactly get it, you would need to go to the apps right here. Yep. So I was like, why is it not working out? Oh, 95. If I wanted to do the 95, well, at this point, and the T is always a little bit larger, it's probably about 1.966 or so. That's just a guesstimate of the T. I'll find the exact T in a moment. Here, I'll show right now where the exact T is. So if you really wanted to know the exact T, you would go to the apps. You would enter in 95% confidence on the T curve. And so you go to 320 degrees of freedom and 95, and look at this. Wow, I was 1 decimal off. Or how close was I? Yeah, it was 1.967. So it's not 1.96, it's 1.967. And this is because as you go higher on the degrees of freedom, it approaches the Z-score of 1.96. So I can kind of guesstimate with so many degrees of freedom, I can basically use the Z-score of 1.96. So it's not exactly, and when we looked up the value, it was 1.967. So JMP is going to carry all the decimals. It's going to do it even further and better calculate than I will by hand. But we can check the top interval right here if we want now by taking the T 1.967 times the standard error, and then we add that to the center of the interval. and we get the upper right there. So that value is the same as the upper, at least the decimal differences at the end are just because I didn't carry enough decimals. So understanding what you're seeing in this output is key right here to know that it has all the notation so you could solve this by hand, but the computer is doing it for you. And I think that mostly has all the work for this. So we did the 4 generic parts. Write-up is accurate and written in complete sentences in paragraph format. So yeah, really not that bad, but the big thing is to know how to interpret these. 99.9% confidence, so that's going to be a very wide interval. 91.5, so you will be using the others. Include a short write-up of the third condition. Of the third condition, one must check. Oh, so it's only the third condition. But doesn't it say down here include the... It does say all 3 conditions. So if the rubric says all 3 conditions, I'd mention all 3 conditions. I'm just saying that. If the rubric says mention all 3 conditions, I'd mention all 3. I follow the rubric. The rubric says do this, do this. Because I'll tell you this much, the graders are going to click these buttons. That's what they're going to click. So I would do what the rubric says. Well, trying to think what else there was. I know some people had questions. I might hop over to Discord for a bit because some people had questions about their data that they might use for their assignment for 320. Yeah. Any other... The graders follow the rubric. Yeah, so you should follow the rubric too. That's why a lot of times I don't even... Because if I'm trying to do a generic version of this assignment, I can't exactly do what you're doing. Horizontal layout, count axis, we did all that. Take a screenshot. Included all that. Include the short write-up right here. Can you look over my data? Yeah, Sam, which one is it? That's why I might hop over to Discord and stuff. Yep, we did all the screenshots. We've done it. The Kaggle data set right there. Where did it go? Sports car prices data set. We might. There might be a problem right here. Well, horsepower. We could maybe make this work. So this week, what kind of models are we making, Sam? Here, we'll go over and we'll talk about this. This week, what kind of models are we making, Sam? What kind of models are we making in 320? What kind of models? BAS 320, Logistic Regression. What kind of models are we making in 320? Let's go check it out. What kind of models are we making in 320? Logistic. And what does logistic require of us? What does logistic require of us? What does logistic require? So when we make a logistic model, which is here in the background, logistic is all about predicting the what of a what. So logistic models, which do we have? I guess I closed down all the notes. Oh no, here it is from Monday or Tuesday. Logistic is about predicting the what of a what. So what kind of variable is used in logistic? Logistic is always a what variable? Predicting probability, correct, of a level of interest for a what kind of y variable. Very key, and actually, I think the notes over here, we got some really good notes on the different types of models. That's from the first class, so here we go. Here it is. So logistic switches 2-level categorical Y. Great job, Sam, right there. So you can see we've drawn out the different models right here. And this is from the notes on Tuesday's class. And so logistic uses the logistic curve right here. And we're showing what happens if we just do basic logistic, logistic with indicators and interactions, versus just general regression here, simple, multiple indicators with interactions. So you've got the differences between the models, and I've kind of color-coded it on what changes, where the indicators change the intercept, the interactions change the slope. Yeah, I will be teaching online, but I will be in person. I'll be in person for 320, 474, and I'll be doing 201 online still. And I think I'm going to do some 207 in person next semester. 207, I love all my classes, but 207 is like, we get to like do like soda taste testing. I do some pretty crazy stuff with 207 because it's a smaller group of students. So we do like Nerf blaster, like measuring contests to see like looking at the variation in Nerf blasters. We do like games. Cool. Yeah. I'll be teaching 201. Tell them to take 201, Jesse. Thank you so much, Jesse. 100 points. And if you're ever interested, whatever you're majoring in, if analytics applies, you can always take like 320 if you can, or 474. One of my students went on to do a PhD in political science, and he took a bunch of our analytics courses. So he PhD, I think he's got his PhD now, PhD political science, and just liked doing analytics. I think analytics is great for all fields, but once again, do what you like. I don't know, it's pretty interesting. Yeah, like one of my students did. Yep, I have students who go to veterinary school. I have students who do PhDs in other disciplines, and I just want you to do what you like. But I believe in data. I think it's a great way to understand the world around us, because let's say we want to predict if somebody is, let's look at the data set here. And so this is how I'm going to make it apply to your data set, Sam. We have right here, Jesse, a data set of students from the year 2011. So I can run a quick code right here called glimpse, which is in the dplyr library. And when I run this glimpse code right here, it's going to give me a glimpse of the data set. So does glimpse make sense on what you're seeing? You're seeing the variable names, then you're seeing some of the answers to the variables. It also kind of tells you what the variable is. Like a factor means categorical. Like factor is just another word for categorical in this world. Integer means quantitative, like quantitative integer values. Double is also another word for quantitative. It just means it takes up twice the space as an integer. Double decimal precision. We go in more detail what that means. But you can see here basically quantitative, categorical, quantitative, like height is quantitative, weight is quantitative. So in this world, we want to predict this week, or what we're doing this week is predicting a categorical. So maybe we could do something like predicting if someone's liberal or conservative. We could predict if someone's born in Tennessee, but it needs to be 2-level categorical. But so Sam, your data might not have 2-level categoricals, but can you turn something into 2-level categorical? Like let's say how much sleep people are getting. I thought I saw sleep. Was there not a sleep variable? So where is it? I thought there was like how much sleep people get a night. Satisfied with weight. Number of texts, fastest car, sleep per night. How much sleep should someone get per night? I think people should get at least 7 hours on average. Like at 6, I'm sure some people can function on 6, but I think 7 is kind of like you're getting enough sleep. Like some people need 8, some people need 9. There's variation, but I would say 7 is a good number to shoot for, and 8 if you can. So, you go to sleep at 10, you can wake up at 6. Good stuff right there. 11, 7. So with this, we have a quantitative variable, which is how many hours of sleep are you getting a night? But we could look at this and say, is this person getting enough sleep? And the answer would be here, yes, yes, no, no, yes, no, yes. Now, this would take a long time to code, but we could go right here and write the code to get it ourselves. So to write this code, we write if else. If else uses a test and then reassigns based on if it passes the test or fails the test. So survey 11 is our data, and we'll type sleep per night is greater than or equal to 7. Then we'll type yes, and we'll type no. So you see it recodes the vector right here. So look at what we ran. Look at survey 11, the sleep variable. Tell me, is it greater than or equal to 7? If it is, return yes. If it's not, return no. We're going to take this, store this into X for the moment, which just puts it as a, we'll just write an X right there so it doesn't go too many lines. This is just going to print the vector now. I'm going to take this vector, store it as a categorical variable, and go to my data frame, survey 11, and say enough sleep. Oops, forgot to store it. Just ran it. And now we've stored that variable in here as the enough sleep variable. So now we have a variable in the data frame, are you getting enough sleep? Now, why is this so important for this week and the way we're doing analysis? I have created a 2-level variable. The 2-level variable is, are you getting enough sleep? Yes, no. So now we're going to predict the probability, and what will it be, Sam? Are we predicting the probability people get enough sleep or the probability people don't get enough sleep? Which one of those are we predicting? The probability people are getting enough sleep or the probability people aren't getting enough sleep? Which one of those are we predicting? Which one of those are we predicting? They are, because it is yes, right? Last. In logistic, the level of interest is last. So you can write this if else right here and then do something to reassign. You can do it all in one step. Like if you wanted to, the way it would look in one step is you would store into the variable here, and then you would do a factor right here. You could open it up there and do this. And this might help make sense of what's going on line by line. So we are storing into survey 11 into a new variable, enough sleep. Great job, Sam, right there. We are making a factor of the if else that runs the test of this. And then inside of here, we have changed to if they do have enough sleep, give set. If there's more than 7 hours of sleep, assign yes. If you don't have if you don't have at least 7 hours of sleep, assign no. It'll run the same thing and create the same variable. It's just I like to do it in steps sometimes to show what we're doing a little bit easier. And so now when we run a logistic, we no longer use LM, we use GLM, which is the generalized linear model. So we're going to write right here, M save into to save our model into an object. GLM for generalized linear model. We're going to predict enough sleep, copy paste to make sure we spell it correctly. And now we can pick a variable. The problem with survey 11, which I've never loved, is it has the X's before it. It's got like X such and such, such and such. So I'm going to do a trick right here called attach. This attaches the vectors to the global environment. So now when I type something like hair color, nope. Oh, we got to type X11 then, right? There it is right there, X11 hair color. Well, let's look at GPA. Like maybe someone's worried that people with high GPAs are not getting enough sleep. Like, does your GPA explain how much sleep you are getting? Data, because this is the X variable. This is the Y variable in this equation. Y tilde X, comma data equals. Now we go to data, survey 11. And then we have to add in family equals binomial because the default for this is the Gaussian normal curve, which is the linear model. So we have to change the family over to logistic 2 level to make sure we're doing logistic regression. That created the model. Now that we've got the model created, we're going to go here to visualize model, and we can see it, and it's probably going to be flat. Yeah, I should have said that before I did it, but I thought it would be. The reason it's flat is there's probably a weak relationship, not statistically significant, which doesn't change the probability much, and that's what I thought I'd see. So there really isn't that. There is not a statistically significant relationship between somebody's GPA and how much sleep they're getting. Frankly, I mean, this is all by random chance, but people with higher GPAs are more likely to get more sleep. Now, most people are getting enough sleep right here. It looks like around, that's 40, that's 60. So around 63% of people are getting enough sleep. And we could check this with a table of survey 11 and enough sleep. And let's go here, length of survey 11. 63%. Oh, whoops. What did I do? That should have been it. Oh, n rows, right? Yeah. There we go. 60. I said about 63. Yep. And that's because if the line was completely flat, it would be the proportion that is yes. Could I make my two-level category cheaper, expensive cars? Exactly. Yeah, Sam, 100 points. Yep. Does that make sense how to use the code that I'm writing right here? So you could you can create your own variable to talk about, like, can we predict a car is cheap or expensive? Because if you predict the price of a car, that's a linear model. But if you predict if a car is expensive, you're predicting like, and you'd say expensive cars satisfy this criteria. What would indicate an expensive car or make something more likely to be expensive? Now, of course, we could have just done a linear model, but if we want to use a data set to show these techniques and practice them and then understand what we're interpreting here, then we could make our own variables. So that's kind of key to what you're doing. Maybe I'll find something better. Trying to think of the best way to do this. I wonder, will it run it with it will run it with gender, right? So let me do the following. Let me cheat. Here's how to cheat when doing analytics. So watch this. What we're going to do is we're going to store from the summary. I think we can get the p-value. There's that. Let's store output. And the output from the summary. Can we just get p-value? Call terms, family. No, we don't want family. Let's just get binomial. Deviance, AIC. Ooh. Well, the AIC will be a good way. Well, I'm going to cheat and use AIC. AIC is how close the model is to the truth. It's one of the last things we learn. So it's not an exact. We're working on 320 right now to end off here. Good to see you, Samuel. 320 right here. This is making more models, and I'm actually going to run every single variable in here. So if you notice all the variables in here, I'm going to run every single variable. There's 51 rows of variables. And so what I'm going to do right here, 51 X's, is I'm going to take this, I'm going to store this into AIC number 1. Yeah, so watch this, Jesse. We need to make AICs first. And there's AICs. And now we're going to run every variable by going here to for loop. This is the power of coding. And we're going to say the variable will be I. It'll go through the vector 1 through 51. This will just change it, so it'll go 1 through 51. We're going to run all the X's, but we're going to limit the X's to only all the rows and then columns I and 52. Column 52 is our enough sleep column, so it's only going to take each time the first and 52, the second and 52. It's going to permutate through those combinations, and then we change this to I right here. And let's go ahead and run this. It looks like it just gave me, that's fine, but I think I got all my AICs. So I just created 51 models, Jesse. 51 different models were created right here. And if I go to which.min AIC, which.min I need to do, I literally said that, model 24. So the 24th variable here is the best variable at explaining. Why is the 24th the best variable at explaining? The best variable at explaining the amount of sleep people get is what? Here it is right there. The best variable at explaining the amount of sleep people get is what? The best variable explaining the amount of sleep people get is the what variable? So take a look at the 24th variable. The sleep you get per night. Yeah, and that's why the AIC is so small. That's the best model. The best way to explain if are people getting enough sleep is to ask them how much sleep they're getting. So that is when it's like, maybe that's not the best variable. I mean, it is. Let's do this. Let's go to make a data set of our things here, and AIC equals AIC. And now we're going to look at this, and we're going to sort by AICs. Okay, the next best variable is variable number 7. So the next best variable, really, the next best variable was GPA. So I picked the best variable in the data set. I went theoretically that GPA is probably impacting people's sleep, but GPA is not statistically significant. Everything we saw with GPA was by random chance. I'd have to go back through the codes and get back to my GPA model, which is right here. And then when we run the GPA model, the differences we see are actually just likely by random chance, i.e. high p-value right here. So same thing works in this world, Jesse, where we have a high p-value, and look at how flat the model is. Now, if you want to see what a good logistic model would look like, this is just a change of what we're doing right here, but here's predicting someone's gender from their height. Notice here the p-value here is super small. That's a p-value of like 0.0000000. So we were able to analyze every variable and say that we really don't have a good way of predicting if someone's getting enough sleep, at least with the data we have. We don't have a good indicator. But this model really does well at predicting the probability someone is male. It doesn't mean you are male if you're a certain height. Like my friend John was about 5 feet tall. He's male, and it would predict he's not male. Like my wife is in this range over here, so it would predict that she's not male. But once again, this is on average over repeated trials. If you have someone who's like 6'3", it's more likely that person is male. I think my probability comes out to like 99% or so because I'm over here on this end of the graphic. You would go up here and trace and print over. But once again, we don't have to solve a lot. In 320, we're not solving everything by hand. You having trouble with your if-else? Can you paste it in the chat real quick? Sam, paste your if-else in the chat. I'll take a look. And then I'm going to run a code here that I need to practice before class. Predict using my model. This will make predictions right there. Type equals response. There it is. Terms. I always forget how to get Logistic to use the predict to give. Oh, yeah. You have to remove the commas. The predict function, here it is. I always forget the one extra argument. Type equals response. Is that not what I typed? Oh, those are are those the probabilities? Are they just so small? I hate scientific notation. Yeah, I think these are the probabilities. Yeah, they are. Okay, I did it right. Type equals response, and then I just looked over it and didn't think I had the probabilities. So you want to delete the commas. So what would we do to delete commas? I think it's I'll try to do this one by memory. We can Google it, but I think it's G sub. So if you have a vector of data, so let's just say here data, and we have here things like, so does this make I'm just making a fake data set, Sam? Does that make sense? Like here's data, but if you notice, that is going to be what? What kind of format is this data currently in? What format is the data currently in? What kind of format is that data currently in? The data is currently what? Well, it's not so CSV means comma separated values. It is kind of comma separated, but what is the class of it, or what is the type? Good answer, Sam, right there. What is the class or the type of that data currently? Hint: the color often shows you. So the color is indicating it's a different class than that right there. So notice how those are blue and those are green. Why are those green? Things in quotes will be what's? We can cheat. We can look over here in the brain of R. Strings, characters. Yep, strings, another word for characters. Great job, Sam, right there. So strings are characters. So I think the code we want to use is gsub. Gsub substitutes stuff in. So we go to gsub, and I don't use gsub every day, but the pattern we are looking for is going to be this, and we are going to replace with nothing, and we're going to do it in the data set of data. There we go. So it looks for that pattern, and then when it finds that pattern, it replaces it. Does that make sense what gsub does right there? So looking at what gsub is asking for argument-wise, gsub says, look for this pattern, replace it with this, and then there's like ignore and other stuff too. But look for this pattern. So I said, look for the comma. It's a little confusing because there's so many commas and spaces. There is the first, and so this reads, I'm doing this wrong. There we go. Okay, it says, look for the comma, replace it with nothing, do it to the data right there. So now we need to overwrite data with this, and then we need to do as dot, let's do as dot numeric data, and store right there. There we go. And what's really neat is, let's say this is something we need commonly. You could take this right here, this sort of function, and run it as a function itself. So if we look at what we have right here, it'd be as.numeric. And then we put this inside of here, and we got data. So this will run, right? Good. And watch this. Function remove commas data return this. There we go. So now if I go here and go to new data, like let's say we have some data right here, which it's got commas. So now I go remove commas of new data. There you go. So I created my own custom function here, which is kind of the neat things we do in 474 especially. So if you look at this, Sam, right here, I have a custom function created that removes commas. It just runs that code. Whatever I input into here gets put into here, and it returns whatever the function runs. So now I have a custom function, which then you have to load your custom functions if you want, or create your own library. So this is kind of how people create libraries, where they have a function that does something like, but I mean, gsub removes anything you want or replaces anything you want. But if you just want to remove commas, you could just have a function that just removes commas for you. You're like, here's my remove comma functions. But think about, if you have like an X, like, do you need a remove X function? Like, you could just change this to like remove X, like remove X. So if you change it to remove what, then like it'll just be like gsub basically, with the second argument being the blank. But now you'd go here and you'd find the pattern X. You'd ignore case or something like that if you want, and that'd be like your remove X function. But commas might be so annoying that you might have your own like remove commas function. Yeah, but I mean, so this just makes our life faster. Time to have like remove commas, and then just removes commas from a vector, and remove commas, and then turns numeric. So yeah, we should make that. Oh, so here, wait. So numeric equals true. And so if numeric right here, then run this. Good. Else it does get the brackets, right? Okay. Doesn't get the brackets. Oh no, we don't even need an else. Oh, the else has to be connected to the if. So it has to be connected at the very end of it. Practicing right here. Yeah. Can work on anything. Replaces anything. Why am I messing up my if else? Else 5. Okay, that worked. Don't want to mess up my code. Unexpected parentheses. Okay, that's the parentheses, right? Yeah, rainbow brackets are nice. Okay, so now, and so it has numeric equals true. Numeric equals false. There you go. So now if someone wanted it to still be numeric or still be character, we added in a separate thing right here where it'll change it. But you can remove anything from it. Yeah. So that's kind of the goal, and you kind of build these things out as you need them. So you come up with the ideas of how you're doing it and what you want it to do. So that way you put in extra things right here, like numeric is set to true by default, so someone doesn't have to enter in a value for numeric when they do it, like whether they want it to be numeric or not. But you can run it such that it returns a numeric vector. Notice how it's not in quotes, or it doesn't return a numeric. Notice how they're still strings. So yeah, that is kind of the neat things we can do with code, and it really makes life easier. So many things we can do. Oh, it's Sam. Great job right there. Yeah. Well, did you notice? Look at this. You know how you said you had an extra parentheses in your function or in your if else? My error was I had an extra parentheses. Sam, 1,000 points. Thank you for working on this right here. Good practice before class here in 34 minutes. But your error right there that you just had is the same error I just had. I had an extra parentheses, and the code said nope. And so I said unexpected parentheses. Oh, it looks like I need to delete it. And I use rainbow brackets right here, which are so cool. Thank you to Adam Spanbauer, who suggested we use these things, because when you do rainbow brackets, you can see where they open and close. Like if you've got a whole bunch of brackets, you can look at the color coding, also selecting one. I can tell you extra comma, so I guess that's why it took you so long. Exactly. Usually run your code in parts. Don't try to build everything. Run it in parts to see if it does what you want and if you're getting the right output. If you're getting the right output, like look at your output, then continue writing more code. If you're not getting the right output, look over what's going on with the output or look at why the code's not running. Remember how I built this code was in parts, not just writing the whole thing at one time. Well, until then, it's the last office hours of the week. Till then, bye for now, everyone. Bye. Class in 32 minutes. Bye.